Thank you. Okay. But luckily, this is the review, so that people who missed this portion still, it's okay. Thanks for reminding me that. You should remind that earlier. Thank you. Anyhow, so this is, the mapping ratio of the length. One-dimensional case is going to be length. The mapping ratio length. When you have a two node like this one, the mapping is going to be uniform. In other words, whatever length map here, next one exactly same ratio is mapped in here. So in other words, if you look at the Jacobian, which is nothing but the length of this one, which is h, divided by length of this one is going to be 2. So this is going to be h over 2. That's why we have h over 2, right? But when you go to higher order element, then Jacobian may not be constant, so that the mapping from one point to another, there are different, the ratio of the mapping. So we'll talk about later. But right now, linear problem, then mapping is going to be 1 to 1, so that this is equal to length in the physical coordinate system, the element divided by the length of the natural coordinate system. Make sense? And if you don't know it, of course, mathematically, you can come up with this one too, but I'm going to give you a little more physical meaning of that one. And then going back to that, example, we talk about it. So this is going to be the test function. So in Galerkin's technique, test function is equal to the shape function. So since we have a linear shape function, so we have a first shape function, second shape function. This should be column vector. And same thing in here, h1 and h2. And then this is going to be u prime, and this is going to be u, of course, multiplied by this one by that, this one by that is going to be u prime and u. So this is going to be a function of c. Of course, this is a constant, but this function of c. And then Jacobian is going to be h over 2. And we integrate negative 1 to 1 in the natural coordinate system. Then we came up with exactly same equation as we derived in previous chapter. So in other words, that this isoperimetric concept does not introduce any approximation. That is exactly same as conventional element. Of course, one-dimensional problem, you may see that we just go through more extra mathematical calculation because that, conventional element could produce this one much quicker. All right. But if you go to 2D and 3D, then you are going to see that that's what we are going to talk about today, that there are really advantage of this isoperimetric element concept compared to conventional element. So before we talk about 2D and 3D, we are going to talk about higher order element. For example, this element is single element, right? One element, but has 3 node points. Previously, we talked about only 2 node points. That's the minimum number of elements. In other words, to define the line, we need minimum 2, the nodal point. But now I can have 3 or 4 or higher, shape of higher order of element in here. So naturally, negative 1 to 1 is going to be 2 nodal points defining the left and right. And third one is going to be in the middle. And again, to make it balanced, then we put this one at the middle so that it doesn't go into one direction or the other, either left or right. So you put in the middle, that makes sense to make more balanced, nature. Then to deriving shape function is, as usual, deriving shape function is same whether this is going to be isoperimetric element, in other words, the natural coordinate system or physical coordinate system. So what you have to do is you say that this is going to be A0 plus A1C plus A2C squared, because that's going to be 3 terms, so that I have quadratic terms. Then when C is going to be negative 1, it's going to be U1. And then if you put this one, A0, A1, A2 this way, this is going to be always 1. So that's going to be negative 1. and then plugging -1 here, and then 2 is going to be 0, so that's going to be 0, 0, and 3 is going to be u sub 3. The third one is going to be plugging 1, so 1, 1, 1, and if you invert this one for this, and then A1, A2, A3, which is going to be 1, C, and C squared, A1, A2, A3. So this is substituted in here, then you come up with the H1, H2, H3, which is going to be something like that. Right? That's the standard procedure to come up with the shape function. And if you look at this shape function also, quadratic shape function so-called, and if you look at this property, -1, 0, and 1. So you got node 1, node 1, node 2, and node 3. Then H1, if you look at H1, when you plug -1, it's going to be 1. Okay? When you plug 0, 0. When you plug 1, 0. So this function looks like this. So 0 at its nodal point, corresponding nodal point, and I mean 1 at corresponding nodal point, this is 1, and 0 at any other nodal point. And if you look at H2, what do you see? When C is going to be either plus minus 1, this is going to be 0. When this is going to be 0, this is going to be 1. So this is H2. This is H1. And H3 is similarly like this. Right? So this property is always true, even higher than element 2. Yes.
The shape functions in this case they were given. The H1, H2, and H3.
This is H1, H2, H3, right? So this is plotting of the H1, H2, H3. This is just plotting of this the equation, the polynomial. Then it shows that this kind of property.
But is that something that's given for like a equation set, or is that something that you have to derive based on the?
That's what it derived in here. In other words, if you look at the one-dimensional shape function, I mean the linear shape function was like this one, right? H1 and H2. Correct? So like 1 and 0, same thing, 1, 0, but now we have more than one nodal point other than itself, so everything have to be 0. So if this is going to be fourth order, in other words, I have a shape function for like that one, then H1 have to be like that. And H2 have to be like this. And H3 have to be like that. And H4 have to be like that. Okay, so one way to develop this shape function is by knowing this property is without going through this tedious process. This is a little tedious. I mean, it's exact, but you know, some calculation. So one way to avoid that is, for example, in here, to develop shape function in this case, what is h1 of x? That's going to be, I know, quadratic shape function because 3 nodal point. So this is going to be have to be 0 here and here. So that means x and x minus 1, or c, in that case c, and c minus 1. So oops, c and c minus 1. So c equals 0, 0, 1 equals 0. So that satisfies, you know, 0 and here, right? And then we have to make sure then at this point, the magnitude have to be 1. So how do I know do that? That's going to be -1, that value, minus 0, and -1, -1. So in other words, this is going to be the nodal point of this one, and those are going to be the nodal point of this one and that one. So in other words, that when this is going to be -1, then it's going to be 1. In other words, that -1 minus 0 is this one, and -1 minus 1 is equal to that one. So which is going to be nothing but 1/2 c squared minus c is going to be same as that one. Okay. Then this one, let's do one more time. To develop this one is that it have to be 0 at here. So c plus 1, because and -1 have to be 0. So that's the, and then c minus 1 have to be 0 here. And then have to be 1 here, so that 0 minus 1 is going to be 1, and 0 minus 1. Then what do you get? That's going to be c squared minus 1, that's going to be -1, right? So that's going to be 1 minus c squared, which is the same as that. So you can develop the polynomial, even high order, using same concept. So there are multiple ways to derive the shape function, yes.
So you're just picking like perfect, polynomials that fit those.
So we know that the polynomial have to be 1 at given nodal point and 0 at every, all other nodal point. We know the property, so that's why we can derive the polynomial in this manner. But obviously, all those polynomial has been developed already, so you don't have to really redo that. But if you try to understand the concept, then that's the way you can do that. All right, so in this case, the mathematical mapping of the geometric mapping is same as, same thing, whether it's the linear element or quadratic element. So, but in this case, 1 to 3, because we have a 3-shape function. So if you take a derivative of this one, so like a Jacobian, this is going to be, x is going to be taking a derivative with respect to c. So take a derivative of that, which is going to be equal to this. And taking a derivative of this equal to that, and derivative equal to that, and x1, x2, x3. So you can see that in this case, the determinant, in the Jacobian, the mapping between natural coordinate system to the physical coordinate system, the length of DC and the length in physical coordinate system, is not necessarily uniform, constant. It's function of C. So depending on what C, your Jacobian is going to be different. In other words, what it means here is that this is, let me redraw here again, C, that, that. So this DC to this dx mapping, and this DC and this dx mapping, J of dx over dc, is not necessarily the same at every point. However, if in this case, this is going to be in the middle, we fix the 0, 0, and 1. So if you fix this one also in the middle, so in other words, x1, x2, x3, and x2 is in the middle, mostly that's what we are going to pick. If you pick in the middle, like x2 is going to be x1 plus x3, and plug into here that expression of this one, then you see that this is going to be constant. In other words, that the mapping is going to be uniform in that case, right? However, if you put this nodal point, so let's put the actual number. So let's say this is going to be 0 and 2, right? And instead of putting this one in 1, if I put in here 0.75, for example, then this that Jacobian matrix is not going to be uniform, okay, throughout the whole domain or mapping from here to here, right? And sometimes we took advantage of that property in some application. For example, in here, Jacobian is going to be C minus 1/2 and x1 plus negative 2c and x2 plus c plus 1/2 and x3. And now let's say, again, to make simplify the equation, let's say this is going to be 0 and that's going to be 1, right? Then middle point, instead of putting at the center, which is going to be 0.5, let's put this going to be 1/4. So put the middle point toward that, 0 side. So 1, 2, 3, 3 node in the physical coordinate system. Then what do you get in here? The Jacobian C minus 1/2, x1 is 0, and minus 2c, x2 is going to be 1/4, and c plus 1/2, and that's going to be 1. Okay, then what do you get? This is 0. That's going to be negative c over 2, right? And then this is going to be c and 1/2. So that's going to be c over 2 plus 1/2, right? That's the Jacobian. Correct? Then, when you look at C is negative 1, what is the Jacobian? Look at the expression. 0, right? Very simple. Okay, then what does it mean? So Jacobian is the mapping infinitesimal length in the natural coordinate system to the physical coordinate system. But now 0 means that disappear. Something disappear. Right? Something disappear. So mathematically, what does it mean? Something disappear. So this is so-called singularity, mathematical singularity. Okay, because the expression is going to be eventually something divided by the Jacobian. So something divided by 0 is going to be infinity, right? So if you have taken some material science class and or fracture mechanics class, then if you have a crack tip, mathematically, then at the crack tip, linear elastic theory, the stress become infinite, mathematically infinite, right? That's what, the fracture mechanics said. So to represent this infinite, people purposely use this kind of singularity concept. So what they do is when they use element, okay, when they use this isoparametric element, so if let's say this is the crack tip, okay, crack tip, in terms of let's look at one-dimensional perspective, then I have an element, after the crack tip, then instead of putting, okay, those are the nodes, I'm going to use the quadratic, element, then in here, that's fine, in here. But if this is going to be crack tip, then instead of putting at the center the regular way, they put the node, purposely put at the quarter point. So they call quarter point, the element. So they put at the quarter length of this one toward the crack tip, so that they introduce singularity at this nodal point, like this one, intentionally, to represent that singularity. Yes.
They said, when there's a kind of like a singularity or like concentration and stress, they move the node a little bit to the side.
Singularity is certainly stress concentration, but slightly different. I mean, stress concentration is yes, but infinite, amount of stress concentration. So usually when you have a hole, if you have a hole, then here you have stress concentration because of the hole, but this is finite, okay? But when you have a crack, then this is basically infinite, so infinite stress concentration. So they don't call stress concentration because of that. So they call stress intensity factor. So they use little different concept. Okay.
Just trying to make sure I understood what you said earlier, though. You said that when there's a infinite stress concentration, where there is supposed to normally be a node, you said something about.
On quarter point. So if you have this one, then element here, for example, along the crack line. So I put not at the center, but put at the quarter point in here when you generate the mesh.
You get that.
So that to simulate this kind of infinity at that this nodal point. Okay. Yeah. This one you don't do that because it's going to be finite. All right, then let's talk about the 2D problem, which is going to be the main meat in chapter 6. So 2D problem, then we have still natural coordinate system and then the physical coordinate system. And natural coordinate system, we have again nicely defined -1 to 1 in the C and eta, -1 to 1. So nice, square shape of element in here. And physical coordinate system is going to be arbitrary quadrilateral shape. So it doesn't have to be rectangle, anything, it's going to be arbitrary. That's the beauty. So any complex geometry we can map with, general shape of quadrilateral, so that we can model those geometry easily. So anyhow, the shape function is like this one we saw in chapter 5, 2D shape function. Of course, in that case, we look at negative B to B and negative C to C in terms of the physical coordinate system. And now this in terms of the natural coordinate system, -1 to 1 and -1 to 1 here. So that's going to be the shape function. Also, I mentioned that to develop the shape function, the simple way is that shape function in 1D multiplied by shape function in also 1D in the eta direction. The product of that is going to give you those 4 shape functions. You know what I'm talking about, right? We talked about it in chapter 5. So we define shape function nicely in terms of the natural coordinate system. So we don't have to worry about shape function in terms of physical coordinate system. Then geometric mapping is same. The x coordinate, y coordinate is going to be exactly mapped using the same shape function. So in other words, what does it mean is that any point in here, let's say this point, is going to be mapped into that point in here. And this point is going to be mapped into that point. Okay, so we have one-to-one mapping from natural to physical coordinate system using exactly same, shape function or interpolation function like that one. And then the solution is also interpolate using the same shape function. So same shape function are used both geometric mapping and variable solution interpolation. That's why we call isoparametric. Same shape function, isoparametric. Then, like we talked about in chapter, previous part of this chapter, we have to calculate derivative respect to x and y. In other words, your Laplace equation is in terms of x and y for 2D problem. So how can I carry out derivative this one in terms of x and y? Because this is going to be function of c and eta. So we have to use this geometric mapping to correlate that. So mathematically, let's say I have a function of phi, which is function of x and y, and x is function of c and eta, and y is function of c and eta. So this is going to be simply mathematical, postulation. So let's say we have function like that, and x is function of that, like that one. Then the d phi of dc, taking a derivative with respect to c, since this is function of x and y here directly, so we have to use chain rule. So d phi over dx, dx over dc, plus d phi over dy, dy over dc, and same thing, d phi over d eta is the d phi over dx, dx over d eta, plus d phi over dy, dy over d eta. So chain rule, but multivariable chain rule. And if you rewrite this one in terms of matrix form, then this column vector is this matrix multiplied by this column vector. Okay, so this matrix is called Jacobian matrix. This is the Jacobian matrix. So Jacobian matrix is in two-dimensional problem 2 by 2. One-dimensional problem is 1 by 1, so just scalar. And three-dimensional problem, Jacobian matrix is going to be expanded into 3 by 3. So that's going to be partial x over partial c, partial y over partial c, and partial z over partial c, if this is going to be 3D, and partial x over partial eta, partial y over partial eta, z over partial eta, and then partial x over partial, how you call this? I forgot. Now the Greek letter. So that's going to be 3 by 3 for 3D problem. This is 2 by 2. In some math book, the transpose of this one, they define Jacobian matrix, but in finite element technique, we define this as a Jacobian. So a little bit different way of saying which is Jacobian. So this is the Jacobian matrix. And so this equation is written as this is going to be Jacobian matrix in here. So if you invert the Jacobian matrix and then pre-multiply both sides, then you get this. You get this one. So if you just define Jacobian matrix is going to be equal R matrix just for convenience, then you got this expression. What this expression is that to take a derivative of the shape function or any function in terms of x and y, you take a derivative with respect to c and eta, and then pre-multiply by this inverse of the Jacobian matrix. So in other words, if you look at this one, okay, R is going to be R11, R12, R21, and R22 in 2D problem. If this is going to be 3D, then of course R13 and etc. So this is going to be R11 times this, R12 times this. So just, explicitly writing in this one. So what it shows that now, let's say phi is the shape function, hi. Then plugging into here, what is that? You want to take a derivative of the shape function with respect to c. What do you have to do? Of course, you calculate that with respect to c and eta, okay? And then multiply by inverse of Jacobian matrix, R11, R12, and R21 and R22. So this is basically the formula to calculate the derivative of shape function with respect to physical coordinate system x, y, or z. If you have a z, then you are going to have one more component. Okay. So if you want to look at this Jacobian matrix, first of all, if you look at Jacobian matrix, just by inspection of this one, you will see that Jacobian matrix is not necessarily a symmetric matrix. In other words, this one and that one is not going to be equal to each other. It could be in some special case, but in general, there's no guarantee that they should be equal to each other. So this is going to be non-symmetric matrix. Okay. So anyhow, if you want to calculate this J11, J12, J21, J22, look at this one. And X is going to be summation of HI and XI. So if you plug into here, then you have to carry out the derivative of shape function with respect to C. So in our case, we have the expression for HI, and which was shown in here. So if you take a derivative with respect to C, that's going to be negative 1/4 times this. So negative 1/4 times that multiplied by x1. And derivative of that 1/4 times 1 minus C, eta and x2. And take a derivative 1/4 times again 1 plus eta x sub 3. And derivative this negative 1/4 times 1 plus C and x4. So depending on x1, x2, x3, x4, because we know that from element, J11 is going to be given in here. And likewise, J12 is y, derivative y with respect to C. So y is going to be this. Okay. So we have to take a derivative. So this is exactly the same as that, right? This is same as this one, except that now xi is replaced by y. So that this is same, except that this xi is y1, x2 is replaced by y2, x3 is replaced by y3, x4 is again replaced by y4. And if you do the same thing for J21 and J22, you got this expression. So this is a general expression. So whatever shape of element, at least quadrilateral element we are talking about, if you know the coordinate of the nodal point, x1, y1, x2, y2, x3, y3, x4, y4, plug into here, then you got the Jacobian matrix. And you can see that Jacobian matrix may not be a constant matrix. In other words, this is going to be a function of, in general, C and eta. Okay, in general. But the special case, for example, what is special case? When you have a rectangular element like this, so your physical coordinate system, your element has a very nice shape, rectangular shape. So the first coordinate is AB, and this one CB, and this one CD, and this one AD. So AC is going to be X coordinate, A and C, and B and D is going to be the Y coordinate here. So if you plug this one into the expression we developed, it's the generic expression here, J11. So X1 is going to be in here, A. So A. X2 is C. X3 is C. X4 is A. Okay. And if you look at that one, then you can see that this cancel out, and this cancel out. So what you get is going to be only this one, which is going to be 1/2 C minus A, which let's say this is the length L, then L over 2. So J11 is going to be constant. Okay, for rectangular element. And if you look at J12, again, J12 from here, what you have to do is you have to plug Y1, Y2, Y3, Y4. What is Y1, Y2, Y4? B, B, T, D. So if you plug B, B, T, D in this expression, B, B, T, D, then you can see that this cancel out, this cancel out, so happen to be 0. Right? So if you continue this one for next two terms, J21, J22, that's going to be 0, and that's going to be the height is going to be H, so H over 2. So your Jacobian matrix is going to be like this, right? For rectangular element. Then inverse of Jacobian matrix is easy because this is the diagonal matrix, right? Diagonal matrix, so that inverse is going to be just inverse of own diagonal. That's the R, R value. Then if you just keep doing this one for derivative now, then R11 and this R11 2 times that. That's what we derived in the one of previous slide. So here R11 is going to be, this is 2 over L, and R12 is 0. So that this term disappear, and this one we calculate from the shape function previously here. Observation with the shape function. Oh, here. Take a derivative with respect to C, which is going to be -1/4 times 1 minus eta. So that this is going to be like that. So you can calculate dH1 over dx. Of course, this is going to be function of C and eta in general. So you got that. So you can continue that for the rest of terms like that. Okay. Then you have very nice expression. Everything is going to be, in that case, linear function of C or eta. And same thing, this is going to be taken to respect to y instead of x. Then use 2, 1 and 2, 2. And this is 0. And this is going to be 2 over h. So this is going to be a function of C. Okay, so again, linear function of C in here, and this linear function of eta. So very nice. So if you calculate this one for Laplace equation like this term, okay, we look at in chapter 5, then in terms of, physical coordinate system, it's going to be like that, A to C and B to D in the X and Y direction. But if you plug this one and that one from the previous expression, so dH1 over dx is this, and dH1 over dy is this. So if you plug that into here and here, then that's the function of C and eta, not function of X and Y. So you have to also transformation of the domain from XY domain into C and eta domain. So we have to use also this mathematical relationship. This is similar to 1D, but this is going to be now 2D, dx dy to dc d eta, and that's going to be the determinant of the Jacobian. So determinant of Jacobian is going to be J is J11, J12, J21, and J22. That's the Jacobian. And determinant of Jacobian is going to be J11, J22, this multiplied by J12 and J21, right? So that's going to be that. And in this case, you got L over 2, 0, 0, H over 2. So the Jacobian is going to be, determinant of Jacobian is going to be this, multiplication minus this So it's gonna be LH over 4. So in other words, this is gonna be nice constant value, LH over 4. Then we can carry out this integral. Of course, this one is gonna be easy to do that even, by hand. A nice negative 1 to 1, the limit, and this is gonna be just cubic quadratic polynomial. So if you carry out this one, that's going to be cubic polynomial and plug into lower and upper limit, you get this one. Then you can see that that expression is exactly same as we developed in chapter 5.2. The reason is why? The reason is the element we are talking about in here is nice rectangular element. So we developed the element matrix for the rectangular element in chapter 5 for Laplace equation. So this is exactly again same solution as what you got from the conventional element. So in other words, the isoparametric element will give you the exact solution as you get from the conventional element. So in summary in here, when you have a nice rectangular shape of element in the physical domain, your Jacobian matrix is going to be diagonal matrix, constant, and 0 of diagonal term. This is going to be, if this is going to be nice cubic shape, then again, same thing in 3D. Constant in the diagonal or of diagonal term is going to be 0. And the term of Jacobian is basically showing the ratio of the area in the natural coordinate system and the physical coordinate system. So in this case, natural coordinate system is negative 1 to 1, 1 to 1. So this is going to be 2, and this is 2. So that's 4. But in the physical coordinate system, there was BC and BD, something like that. So this was L and this was H, right? So area is going to be L times H. So this is going to be LH over 4. That's going to be the determinant Jacobian. In other words, this one also means that when you have a nice, shape of this element in the physical coordinate system, when you have this area, dc and d eta is going to be mapped into this area, dx and dy, okay, and the ratio is going to be uniform and is equal to this ratio. This for nice shape of the rectangular element. However, I'm going to mention one thing and then we'll take a break. If your element looks like that, so slightly, change from the rectangular shape. In other words, this is the rectangular shape, right? But now it's not rectangular anymore, like a little bit trapezoidal shape. Small change, okay? If you have that one, then all this nice feature we talk about is not going to be true anymore. So even integration of this one, analytical integration is going to be really a hassle, right? That's why now you see that the formulation of this isoparametric element, and then eventually we can carry out this one using numerical integration. So how complex the shape is, still we can carry out that numerically, and then we can calculate the element matrix. So let me stop here, and then we'll take a short break. Any question up to this point? All right, then let me stop recording.